welcome back. So this is the second lecture on the chapter of mathematical induction. In the first chapter we covered some theory around like what is the mathematical induction, what are the different steps that you need to take to solve a typical problem in mathematical induction. Now here in this what we are going to do is we are going to take some examples and we'll solve some problems. So let's start with some basic problems here. We'll be covering it from NCERT here this time. So the first one is we have 1 plus 3 plus 3 square plus 3 to the power n minus 1 is equal to 3 to the power n minus 1 by 2, right? So just quickly recap few things. So what we used to do was for solving this, for n epsilon natural numbers, we need to prove that this equality always holds true, right? So the first step again, the starting point is here. We can see like this. So 1 is nothing but 3 to the power 0. So starting point is n is equal to 1. So let's prove this is true for n is equal to 1. So when we put it n is equal to 1, we get 3 to the power 1 minus 1, that is 3 to the power 0, which is equal to 1. This is the LHS, and the RHS on the same side. Same time it becomes 3 to the power 1, that is 3 minus 1 by 2. This is nothing but equal to 2. So we see for the starting point, that is n is equal to 1, this equality is true. So what is the second step? Let's assume that this is true for n is equal to k. For n is equal to k, which is greater than 1, let's assume that it is correct. That it means 1 plus 3 till 3 to the power k minus 1 is equal to 3 to the power k minus 1 divided by 2. So let's assume this is true. So let's assume this, and using this assumption we need to prove the third point, that is for n is equal to k plus 1, right? This equality is true, right? So this we need to prove. So what is this? This becomes again 1 plus 3 plus 3 to the power k minus 1, right? And this whole plus 3 to the power k plus 1 minus 1 is nothing but 3 to the power k, right? So this is something that we need to prove to be equal to 3 to the power k plus 1 minus 1 whole divided by 2, right? So now what happens is simple, that we have done many times. So let's replace this value here. So what happens is, I know this thing is equal to this. So the thing that finally I need to prove is that 3 to the power k minus 1 divided by 2, this is the value of this entire bracket, plus 3 to the power k is equal to 3 to the power k plus 1 minus 1 whole divided by 2. This is something that I need to prove. Okay. So now I am removing this part and moving it here, right? So what I need to prove is, that this thing is equal to this thing. Very simple. Let's take the LCM. It becomes 3 to the power k minus 1 plus 2 times 3 to the power k whole divided by 2, right? This is the LHS. I am just taking the LCM. So this is nothing but 2 plus 1 is equal to 3 into 3 to the power k minus 1 whole divided by 2. So I know that a to the power x to the power a into x to the power b is equal to x to the power a plus b. So here x is 3, so it becomes 3 to the power k plus 1, the power x minus 1 whole divided by 2, which is nothing but the same as here, right? So I am able to prove just by simply replacing that. Okay, this equality is true for n is equal to 1. Assuming that it's true for n is equal to k, I am able to prove that this is true for n is equal to k plus 1, right? So that's a typical step that we discussed in the last lecture as well, and we continued here as well, right? So that's the first question that we solved, a pretty basic one. Now let's take another example. Again, let's take a straightforward question that says 1 cube plus 2 cube plus n cube, right? This needs to be proved to be equal to n plus 1 by 2 whole square, right? So this is something that I need to prove. Okay. Again, starting point is n is equal to 1. So let's see if it is true. So when I put n is equal to 1, I simply get LHS is equal to 1 and RHS equal to, let me put 1 here, 1 into 2 So this is 1 into 1 plus 1 2 upon 2 whole square, that is nothing but 1. So this equality holds, right, for the starting point, right? So now second point, let's n is equal to k, which is greater than 1, and let's replace it here. So I assume that 1 cube plus 2 cube up till k cube is nothing but equal to k plus 1 by 2 whole square, right? So that's something that I know. Let's assume this is correct. Let's assume this is correct. Now for n is equal to k plus 1, right? So what happens is, I do 1 cube plus 2 cube up till k cube, right? This is the bracket, plus k plus 1 cube, right? So this is the LHS, right? So let's simplify it a bit further. Simply again replacing this value here, right? Replacing this value here, what I get is k plus 1 by 2 whole square, right? And this is again k plus 1 whole cube, right? This is something that I get. Now this is the left hand side. Let's see what is the right hand side here. So right hand side is equal to, when I put n is equal to k plus 1, I get k plus 1 into, this becomes k plus 2, right, upon 2 whole square, right? So one thing is there, I am able to see a 2 square here, so I know that I have to take an LCM, nothing else that I can do. It's k square, k plus 1 whole square plus 2 k plus 1 whole cube, and that thing divided by 2, right? This thing needs to be, and that thing divided by 2 square, so this has to be 2 square, right? So this 2 square will reach here as an LCM, and it will be 2 square here, and this needs to be proved to be equal to 2 square. So this thing is square. So what I need to do, essentially I can cut this part, right? So I need to prove that numerator of these two parts are same. So again, I know I can see a term of k plus 1 whole square here. So let's take out k plus 1 whole square, right? And this things become k square, right? Plus 4 times k plus 1, right? This is something that I am left with. Okay? That's all. Now when I see this, it becomes k square plus 1 plus 4k, right? K square plus 4 plus 4k, right? So this is nothing but k plus 2 whole square, right? A square plus b square plus 2ab. So I get k plus 1 whole square into k plus 2 whole square. So this becomes k plus 1 whole square into k plus 2 whole square, right? And this is what I needed to prove. So again, a direct imputation, and I am able to solve this question. Again, a fairly straightforward question. We might not recall this answer as well. So it says a plus ar square, right, till ar to the power n minus 1 is equal to a times r to the power n minus 1 upon r minus 1, right? So this is called a GP. So it's saying that the sum of n terms of a GP is given by this. So we might read this geometric progression later on, right? But this we have to prove that for n is equal to 1. So let's assume, so let's start for n is equal to 1, right? So what happens for n is equal to 1, I can see, okay, so this becomes a, when n is equal to 1, then r to the power 0 is 0, so it becomes LHS is a, and RHS equal to, when I put n equal to 1, I get r minus 1 and r minus 1 cancel, so it becomes a. So this is true. For n is equal to k, which is greater than 1, left hand side becomes, let's assume, so what I need to assume, it's that a plus ar plus a r to the power k minus 1 is equal to a r to the power k minus 1 upon r minus 1. So let's assume this is correct. So now for n is equal to k plus 1, what happens is, I get a term, in addition to this, I get a plus ar plus a r to the power k minus 1 plus a r to the power k, right? So when I get k is equal n is equal to k plus 1, 1 and 1 cancel, so I get this thing. Again, this is direct imputation ideally, right? So let's put it here. So it becomes a r to the power k, I am putting this value, minus 1 upon r minus 1 plus a into r to the power k. That is the left hand side, right? And what's the right hand side? So right hand side becomes, when I put n is equal to k plus 1, it becomes a r to the power k plus 1 minus 1 upon r minus 1, right? Upon r minus 1, right? That needs to be proved, right? I know r minus 1, let's take the LCM. So what I need to prove is essentially a r to the power k minus 1 plus a r to the power k, when I take the LCM, r minus 1 is equal to a times r to the power k plus 1 minus 1, right? I'm just cancelling out the denominator after taking the LCM. So now let's see what I can see here, right? So let's multiply, let's open the bracket. It becomes a r to the power k minus a, opening this, plus a r to the power k plus 1, right? That is r to the power k plus 1 because r to the power k into r, minus a r to the power k, right? This into minus 1. I can see now these two terms are cancelling out each other, right? So these are cancelling out, and I can take a common here, a r to the power k plus 1 minus 1, right? So this is what I need to prove, right? So this is again a straightforward question wherein I just needed an imputation. However, the result is interesting and we can remember the result here. This is some for an GT. Okay. Now let's move a bit further and let's see, if we can take another good problem here. Okay. So what we need to prove here is, let's see, 1 plus 2 plus 3 plus up till n, right? The sum of first n whole numbers less than 1 by 8 of 2n plus 1 whole square, right? So this I need to prove. Again, quickly, when I put n is equal to 1, LHS is equal to 1 and RHS is equal to 2 plus 1, 3, 9 by 8, right? That becomes 9 by 8. Of course, 1 is less than 9 by 8, so this is correct. This is a fraction which is greater than 1, right? Now let's assume for n is equal to k, which is greater than 1. I am assuming it to be true. So what I am saying is 1 plus 2 plus 3 plus k. So sum till k is less than 2k plus 1 whole square upon 8. So that, let's say this is less than so this is something that I know. Now what I need to prove is 1 plus 2 plus 3 plus k plus 1 is less than 2k plus 2 plus 1 whole square upon 8, right? I'm just writing 2k plus 1 as 2k plus 2 plus 1, right? So I'm just writing this. Now I know that this thing, right? That's this thing is definitely less than 2k plus 1 whole square by 8, right? So there are two things that I can do. Okay. So what I can do is let's add. So let's do it this way. Let's call this thing as P, okay? And I am saying that if I add a constant C, this becomes equal to 2k plus 1 whole square upon 8. Let's say, wherein we say C is greater than 0. C is a positive number, and if I add a positive number to this entire thing, which I am calling as P, I am calling this as P. Okay, so I am calling P plus C is equal to 2, 3, and where is C is greater than equal to this, right? So let's write it. So this was P. I called entire thing as P, right? Plus K plus 1. So I am adding K plus 1 to P, right? And which I am okay. So what I am doing is, and I have to prove that this is less than or equal to 2k plus 3 whole square by 8, right? This is something that I need to prove, right? Now what is P? P is nothing but, let's replace the value. P is 2k plus 1 whole square divided by 8 minus C, right? I am replacing the value of C here. where c is okay plus 1 is less than 2k plus 3 whole square by 8, wherein c is greater than 0. This is I know. This is something that I know, right? So let's do something quickly. Let's take the LCM. So it becomes 2k plus 1 whole square minus 8c plus 8 is less than, I'm taking the LCM and cutting the denominator, is less than 2k plus 3 whole square, wherein c is greater than 0. This is an assumption, right? So now let's quickly open it. It becomes 4k square plus 1 plus 4k, right? Minus 8c plus 8 is less than 4k square plus 9 plus 12k, right? This is something that I need to prove. This gets cancelled, right? This gets cancelled. Okay. So what I essentially get, this also gets cancelled. This 9. So what I get is that minus 8k is less than 8c, right? This is something that I get, which essentially means that if I take it in this way, c plus k is greater than 0, right? And this I know definitely is true. Why this is true? K is greater than 1 and c is greater than 0. So this is always going to be greater than 0 and there is no contradiction. Hence I can see that okay, this is also true, right? So there is an alternate way that I took. So whenever I get an inequality, what I do is I convert it into an equality by adding a constant c, which is greater than 0, and then I move ahead with the proof, right? So that's another way of proving some questions which are like, which involve inequality here, right? Okay, so now taking another tough question, I think this is a good one. So what I need to prove is that x to the power 2n minus y to the power 2n is divisible by x plus y. This is something that I need to prove. So let's assume first of all for n is equal to 1, LHS becomes x square minus y square, right? Which can be solved as x plus y into x minus y, right? Typically I see like if there is a factor of x plus y, then this is true because this is divisible by x plus y, right? Now let's assume for n is equal to k, let's assume that x to the power 2k minus y to the power 2k is some multiple of c times multiple of x plus y, right? Let's assume this. This is assumption. Now what I need to prove is that x to the power 2k plus 2 minus y to the power 2k plus 2, that is I am replacing k plus 1, is some multiple, this is c2, this is c3 of x plus y, right? This is something that I need to prove. Okay, so let's do something. Let's use this equation, right? Let's use this because I have to use this equation and try to prove this thing. So what I do is x to the power 2k is equal to c, I'm still calling it as c, or let's call it c2 times x plus y to the power 2k. This is correct. I'm taking just y to the power 2k that side. Now let's try to create this thing. Can I create this thing? For that, what I need to do is I just need to multiply by x square. So when I multiply this by x square, it becomes x 2k plus 2, right, is equal to c2 times x square x plus y to the power 2k x square, right? This is correct, right? Now I create this thing. So what I do is x to the power 2k plus 2 minus y to the power 2k plus 2, right? This is equal to c2 times x square x plus y, keeping this thing constant, right, plus y to the power 2k x square minus y to the power 2k, and I am writing this y to the power 2k plus 2x, this y square, right? This is fine. Now let's play with the right hand side. This is c2 x square x plus y, right, plus y to the power 2k x square minus y square, right? Now I know this is nothing but x plus y and x minus y, right? So now what I can see is there is a term of x plus y in this and there is a term of x plus y in this, so that means this is also divisible by x plus y. So I assume that okay, this is divisible, that means this from here I took this value and I created this term and I found that everything is correct, right? So that's a good way of solving this inequality problem. So there are two ways. If there is a divisibility thing, let's assume that there is a C2 which is an integer and then replace everything. And likewise, if there is an inequality, just add a positive number to make the inequality as an equality, right? Okay. Okay. Perhaps the last problem that we are taking for induction. What we need to prove is that 2n plus 7 is less than n plus 3 whole square, right? This is something that I need to prove. Okay. So now, when n is equal to 1, I get 7 plus 2 is 9 is less than 3 plus 1, 4 whole square, that is 16, which is correct. Okay, this is correct. Now, for n is equal to k, which is greater than 1, it becomes 2k plus 7 is less than k plus 3 whole square, right? This is, let's assume this is correct. Now, for n is equal to k plus 1, what I need to do is, let's take it in this way. It becomes 2, I replace k plus 2 plus 7, right? This needs to be proved to be, to be less than k plus 1 plus 3 is 4 plus 4. So let's write it individually, k plus 1 plus 3 whole square, right? Again, the thing that I told, like, let's convert this. So let's convert this in inequality. So it becomes 2k plus 7 plus c is equal to k plus 3 whole square, wherein c is greater than 0. Any quadratic number, when I add to left hand side, it becomes equal, right? So now let's see what happens. Okay. So I have this thing. Let me open this thing. Okay. So it becomes 2k plus 9 is less than k plus 3 plus 1 whole square. So I am writing it as k plus 3 plus 1 whole square, and I open it as a plus b whole square. So it becomes k plus 3 whole square plus 1 plus 2 times k plus 3, right? It becomes like this. Now I know that k plus 3 whole square is something like this. So I replace it as 2k plus 7 plus c plus 1 plus 2 times k plus 3, right? And this actually needs to be less than or greater than 2k plus 9. This is something that I need to prove. Okay. So simply let's cut it down. Okay. So it becomes 9 is less than 7 plus 1 is 8 plus c plus 2k plus 6, right? So this is 8 plus 6 is 14 minus 9. So I take 9 there. So this becomes 2k plus c plus 5 is greater than 0. Now let's see, is it true or not, right? 5 is a positive number, right? C is a positive number which is greater than 0. I assume that k is greater than 1, right? So this is always going to be greater than 2 and this is always true, right? So what I did was I convert this inequality into an equality by adding a c here which is greater than 0, and I then replace the value here and I found that there is no contradiction here, right? So this is true. So what happens is, guys, these are the few examples that I took. So there are simple ways, like when we have an equality, simply replace the value and then prove that there is no contradiction. If there is an inequality, let's add some positive number on the side which is lesser and make it equal. And if there is a multiplicative thing that we have to prove, that is divisibility, let's assume that it's an integer that can be multiplied to make it like an equality. So ideally what we do is we try to convert everything to an equality and replace the value and try to prove that there is no contradiction, right? So these are the few problems that we took, and hope you like this video. We will then cover the next chapter 5 from NCERT in the upcoming videos. Thank you.